Hey there, everybody, all my classmates or whoever. This is Dorothy, and I figured the best way for me to study for this exam is to do my best to teach other people how to do it. This may get posted, this may not, whatever. It's fine. Just before we get started, yes, I have music on because the silence is too much, but at the same time, my parents are leaving for Guatemala tomorrow, so it may get a little chaotic in here. Please bear with me, and hopefully if you need any help, this will make sense to you. Okay, so for this first problem, we have a system that has a piston and cylinder device. Okay, from what I understand, that means we've got a piston and a cylinder. Gee, imagine that. Okay. So, in this system, the piston can give me a second to get another color. The piston can move up and down. This is producing work. So, work is transmissible, and heat can also come off of it. Okay? But the fluid itself is stuck inside. Can't go anywhere. This is the definition, pretty much, of a closed system. So a reciprocating air compressor is a closed system, and you would treat it as such. Alright, in case you can't tell, I am having to stoop to use Paint to make this video because various other programs on my computer PowerPoint are choosing not to work right now, and it's just got issues and stuff, so I am using Paint for this. Forgive me for the limitations here. Alright, so this question is asking if the enthalpy of vaporization, also known as the latent heat, does it change with pressure, and how does it change? Well, enthalpy is one of those things that has always really confused me, and I don't know if it's confused you, but so far the best general explanation I've gotten is that enthalpy is chaos, a measure of how much chaos is in a particular system. Okay, so a really simple way to test the pressure change in a system is to consider the matter as a liquid and the matter as a gas. Let's just label it like this. Yes. So we have a gaseous fluid of some sort. Whatever. Anyways, so what is the pressure at some particular point, P1? Well, let me first explain this. We have, obviously, never mind, that was circular logic going on in my brain for a second. So at this particular point, we have a pressure. This is rho GH, as I'm sure many of you are sick of hearing about. Now consider that exact same point in a gaseous form of the same material, the same mass. Well, the pressure here is going to be a lot less. So we can conclude that the pressure from the liquid state to the gaseous state is decreasing. In general. This is generally true if all of the things being equal, pressure is decreasing. Alright, now what about the enthalpy, the chaos of the system? Well, we all know that liquids are much less prone to leaving. You put water in a cup, it'll stay there more or less. The liquid form will, anyways. Some of it will evaporate and just float off into the ether, and you'll have no idea where it is, and it will just be. And of course, we've got all these little particles zooming around and stuff, and we don't have that in water. So, as we go from this system to this system, the enthalpy is decreasing. Excuse me. is increasing. My brain is somewhere else today. Alright, so we can conclude that as pressure increases, the enthalpy of vaporization, in particular, is decreasing, because that's the inverse of this relationship. And the relationship we already have, as P decreases, the enthalpy will increase. And that's the answer to this question. Real quick, something else that I forgot was that when I was doing this problem in class, sorry about that, I forgot this thing has a wire on it, and I hit the wire. Okay. So I hit the wire and it fell. Anyways. Something I forgot is that when I was in class, I had no idea. I actually came up with this whole concept kind of in reverse order. I came to my conclusion, and then I was like, oh, well, I could look at it this way too. So how did I find out the other way? Well, the way I did it the other way was to look at one of the many tables that we have. Go to one of the saturated tables. Let's say A7, I think. No, not A7, A4. No, we want it, this is giving it in terms of temperature, we want it in terms of pressure. So we got the pressure here. There we go. Let's zoom in a little bit. Okay, a little too much. Okay, that was pretty much useless. Give me one more second. Okay, there we go. Alright, for given pressure, let's say 4.0, we can find the enthalpy of vaporization. It's right here. That's about the 2400 range. Okay? And then we've got the pressure increasing to 15 kilopascals. And the corresponding enthalpy of vaporization is in more of the 2300 range. Therefore, we can conclude that as this pressure is increasing, this enthalpy is decreasing. Excuse me. It's decreasing. My directions are just all messed up right now. I'll be back in a minute with the